Hello everyone. In this video lecture we will focus on elimination molecular from conjugate base and elimination unimolecular reactions. In previous lectures we have discussed elimination by molecular reaction, its salient features, mechanism, orientation, structural requirements, etc. Now, having learned the idea of elimination reaction, this is a continuation of the earlier elimination reaction. So the second pathway that is often observed for elimination of alkyl halide. Let's focus on this. So the heading is E1cB. So let's start with salient features and the significance of this. So this stands for elimination unimolecular from conjugate base. So E stands for elimination, 1 stands for unimolecular reaction, C stands for conjugate, B for conjugate base. So in this reaction, look at this, molecularity of the reaction is 1. So this 1 stands for the molecularity of the reaction. This does not stand what is the order of reaction. So this 1 stands for total molecularity of the reaction is 1. That means only one molecule is involved in the rate determining step of this mechanism. In this E1cB mechanism, carbon hydrogen bond breaks first, followed by breaking of carbon halogen bond. So in this E1cB, first carbon hydrogen bond has to break, followed by breaking of carbon halogen bond. This E1cB reaction occurs in two steps. So this is a two-step reaction. Reaction occurs in two steps. In the previous one, E2, reaction occurs in single step, that is concerted or single step reaction. That reaction was molecularity 2. In the first reaction, both CH and CX bond break simultaneously in the single step. Look at this. Here the reaction is two-step reaction. The reaction occurs through carbanion intermediate. So in this reaction there is a formation of carbanion intermediate. So intermediate formation is a very important step for this E1cB mechanism. Kinetics for this reaction, the rate of reaction is equal to some constant known as specific rate constant into concentration of alkyl halide into concentration of base. So reaction is first order with alkyl halide and the first order with base. So order of reaction, this is 2. First order with respect to alkyl halide, first order with respect to base. So total order of reaction is 2. So molecularity is 1, order of reaction is 2. So if you look at this red equation, the red is directly proportional to base. So the reaction requires a strong and concentrated base. So all these E1cB reaction must be carried out in presence of a strong and concentrated base. If the base is a weak and a dilute, then the rate of reaction will be very slow. So to increase the rate of reaction, we must have a strong and the concentrated base. Now for this E1cB reaction, elimination from conjugate base, the requirement of solvent, because again solvent plays a very important role for this E1cB. So the solvent has to be polar aprotic solvent. So the role of solvent is polar aprotic solvent must be used for this E1cB mechanism. The order of reactivity of alkyl halides. We have R, F, RCl, RBr, Ri. So look at this, we have different halogens. Alkyl group remains same, halogen remains different. So if we have different alkyl halides, the most reactive or the fastest reaction is with alkyl fluoride. So alkyl fluorides are the most reactive for this E1cB, followed by alkyl chloride, followed by alkyl bromide. So if you look at it, this is just a reverse of the reactivity of E2. Now suppose we have same halogen but different alkyl groups, then the reactivity says primary alkyl halide is the most reactive, followed by secondary alkyl halide, which is more reactive than tertiary alkyl halide. So again look at this, primary is the most reactive and secondary is the tertiary is the least reactive. So this is the order of reactivity of halogens for this E1cB. Now this E1cB reaction, orientation of the product form. Orientation of the product formed is Hoffman. So Hoffman will be forming as a major product and the Sijeff's elimination product will be forming as a minor product. Whereas in case of E2, Hoffman was forming as a minor product unless there was some sterically hindered system or if the base was sterically hindered. But in case of this E1cB, Hoffman will be forming as a major product and the Sijeff's will be forming as a minor product. So if you look at this reaction, as I told you, this is the least common reaction. Okay. Now in this reaction, breaking of CX bond is the rate determining step of the reaction. So in the rate determining step of the reaction, there is a breaking of CX bond. So look at this. in E2 reaction there was a transition state, and transition state acquires alkene character, whereas in E1cB there is formation of carbonyl intermediate and there is no considerable alkene character in the transition state. So these are some of the important features or important points concerning this E1cB. Now this E1cB reaction, the rate of reaction or the reaction does not show primary kinetic isotope effect, meaning thereby the rate determining step does not involve breaking of carbon-hydrogen bond. So let's go to the mechanism, because all these features will be clear when we discuss the mechanism of the reaction. So coming to the mechanism of this E1cB, mechanism of the reaction. So we have looked at this. We have an alkyl fluoride, because for this E1cB reaction alkyl fluoride was the most reactive. So we are taking the help of alkyl fluoride. So this is alpha carbon, this is beta carbon, this is 1 carbon, this is 2. Now we are reacting with a base B minus. So this is the first step of the reaction. So in the first step, this B minus abstracts this acidic hydrogen, and this electron pair which was sharing between beta carbon and hydrogen is transferred to beta carbon, and this gives you carbanion, that is C minus. So this is carbanion intermediate. In the second step of reaction, these carbanion negatively charged carbon, so the electron present on this carbon push out this halogen, that is fluoride, from the system, and this gives you the product alkene. Now if you look at this, in this RDS, this is the RDS rate determining step. So in this rate determining step, only one molecule is involved, that is carbon, and so the reaction is molecularity. Now look at this, this is acid, then this is conjugate base. If you look at this, this is acid, then this is conjugate base. Now elimination is occurring from the conjugate base, so hence the mechanism is known as elimination from conjugate base. Why this is known as unimolecular? Because look at this, the rate determining step or the slowest step of reaction involves elimination from conjugate base, so the only one molecule is involved, so this is known as unimolecular. Why reaction requires very strong base? Because this carbon hydrogen bond being almost non-polar, this hydrogen is mildly acidic, so we require a very strong base so that this is converted into the carbanion. Now in one of the features we have said the most reactive for this mechanism is the primary alkyl halide is the most reactive and the tertiary is the least reactive. So now look at this, in the intermediate there is a formation of carbanion, and if you look at the stability of carbanion that we have discussed in the 11th class, so the stability order of carbanion is primary carbanion is the most stable, followed by secondary, followed by tertiary. This is stability order of anion. carbanions. So since primary carbanion being the most stable, so the primary carbanion formation should be the fastest reaction. So the reactivity of alkyl halide is parallel to the stability order of carbanion. Primary carbanion being the most stable, primary alkyl halide is the most reactive. So this is for the first point, why primary was the most reactive. The reason, the intermediate carbanion primary is the most stable. So write down stability of carbanion is parallel to the reactivity order of alkyl halides. Now again in the same feature we also said alkyl fluoride was the most reactive and alkyl iodide was the least reactive. So the reason being, this F minus, so F minus fluoride ion being the strongest base of all the halide ions. So we have fluoride, chloride, bromide, iodide. So out of these, fluoride ion being the most basic is a very poor leaving group. So this fluorine carbon bond being the stronger bond, its tendency to break is less. So fluoride ion being a very strong base is a very poor leaving group. So this, before this carbon fluorine bond breaks, this base abstracts carbon and hydrogen and acquiring carbon, and finally this free electron is attacking this carbon bearing fluorine and helps in removing fluorine. So the reason for this is fluoride ion being the strongest base is a very poor leaving group. So these cannot be eliminated in the concerted or single step reaction. So F minus being a very strong base is a very poor leaving group. So this is the reason why alkyl fluorides was the most reactive and iodide was the least reactive. So now look at this. This is alkene. Now one the feature also says orientation factor. Means if there are two possible beta hydrogens that could be removed from the molecule, then the orientation says reaction favors Hofmann product, not Sages product. So these again can be explained based on the stability of carbanion form. So let's take up this. So this is the mechanism. Now coming to the orientation part. So let's take this CH3, CH, F, so we have this compound. So this is alpha carbon, so this is beta 1, this is beta 2. So we have two types of beta hydrogen. So now look at this. This reacts with sodium ethoxide, so which is a strong base, sodium ethoxide in alcohol, ethanol. Now look at this. These on the reaction with strong base, two possible carbon ions should be formed. So look at this. Removing of beta 1 hydrogen gives you CH2 minus CHF, CH3, CH3. So this is one anion. If you look at this anion is primary carbon ion. On the other hand, removal of this beta 2 hydrogen, this will give you CH3, CHF, C, CH3, CH3. Now if you look at this carbanion is tertiary. So if you look, so now we have just discussed the stability order of anion is primary is the most stable, tertiary is the least stable. So we have primary anion and tertiary. So this is more stable. Now this being the more stable, elimination from this side will give you the major product. So that is CH2 double bond CH, CH3, CH. So this is Hofmann product which is forming as a major product because this is coming from the more stable carbanion. Because the more stable anion, because out of these two possible anion, the more stable anion will be forming in a larger quantity. If this anion is forming in a larger quantity, the elimination product from this more stable will be forming as a major product. But this product is Hofmann product. We have only one alkyl substitution here. On the other hand, if the elimination is from this less stable tertiary carbanion, this will give you the Sages product which is forming in a small amount. So this is Sages. Look at this, we have 1 alkyl, 2 alkyl, 3 alkyl. So this is Sages product, but this is forming as a minor product. Why this is forming minor product? Because this tertiary anion being very unstable, this is formed in a very small quantity. If the anion is forming a very small quantity, the product from this anion will be very small quantity. So this is the orientation of E1cB. So this E1cB, so the question says if we have more than one beta hydrogen, then the orientation will always favor Hofmann, that is the least alkyl substituted product will be forming as a major product. So this is specifically from alkyl fluorides. In case of chloride, bromide, iodide, normal reaction gives you Sages product unless there is sterically hindered system in the structure of the molecule, or if the base is sterically hindered, only then the reaction will favor Hofmann, otherwise that will favor Sages product. So this is a brief of discussion about the E1cB mechanism, that is second mode of elimination of alkyl halides. Now after this we are left with one more pathway, that is E1 pathway. So let's discuss this E1 pathway, then I'll go to the comparative study of these three pathways. So we are taking up E1 elimination, that is the third pathway. So E1 stands for E for elimination, 1 stands for unimolecular. So the molecularity of the reaction is 1. So elimination, unimolecular. Molecularity of the reaction is 1. This reaction occurs in 2 steps. This is 2-step reaction, occurs in 2 steps. This reaction occurs in 2 steps, and reaction E1 reaction occurs via formation of carbocation intermediate. Carbocation intermediate formation is there. Formation of carbocation is the rate determining step. Formation of cation, that is carbocation, is your RDS. Rate determining step is the one in which there is a formation of carbocation. Now this reaction, in this reaction, CX bond, carbon halogen bond, breaks first, followed by carbon hydrogen bond. So in the E2 there was simultaneous breaking. E1cB for CH bond followed by CX. E1 for CX followed by CH bond. Now this reaction, E1 reaction, all E1 reaction must be carried out in presence of polar protic solvent. Solvent should be polar protic. So polar protic means we can have, look at this, methanol, we can have water, etc. These are known as polar protic, means acidic hydrogen is attached to oxygen. So these are known as polar protic solvent. So all successful E1 reaction must be carried out in presence of polar protic solvent. Now coming to kinetics of this reaction, the rate of reaction is equals to rate into concentration of alkyl halide So if you look at this reaction is first order with respect to alkyl halide and zero order with respect to base. So now look at this. The reaction rate equation is independent of base. That means all this E1 reaction is either carried out in presence of a very weak and dilute base or in absence of base. So in most of the case, the solvent itself act as a base for this E1 reaction. That means if we change the nature of base, then this base does not have any bearing on the rate of E1 reaction. So this is independent of base, and if you look at this, the order of reaction is 1. This is first order reaction. So this one doesn't mean the order of reaction is 1. This one means the molecularity of the reaction is 1. The reaction occurs in presence of absence of base or in presence of a very weak and dilute base. Either if you have to use base, then the base should be very weak and should be dilute, or in most of the case the base means the solvent which is used for the reaction will itself act as a base for this elimination reaction. Now in this E1 reaction, the orientation is always Saint-James. Orientation is always Saint-James. That means the more alkyl substituted, alkene will be forming as a major product. Now coming to the reactivity order of different halogens for this E1. Reactivity order of different halogens. Now in this Ri, alkyl iodide is the most reactive, followed by alkyl bromide, followed by chloride, followed by fluoride. So this is the most reactive and alkyl fluoride is the least reactive. Now in case we have different alkyl group, then the most reactive is tertiary alkyl halide is the most reactive, followed by secondary alkyl halide, followed by primary alkyl halide. This is the reactivity order of alkyl halide. Now this reactivity order can be explained by invoking the concept of stability of carbocation. So this we can explain later on. So this is some of the important features of E1 reaction: elimination, unimolecular reaction. Now coming to the mechanism, because by use of this mechanism we can explain all this behavior or important phenomenon, features that is observed. So coming to the mechanism part, so we have looked at this. This is alkyl halide. The first step of this reaction, this is the rate determining step, which is an equilibrium step. This is RDS, and the reaction is carried out in presence of polar protic solvent or methanol. When look at this, CX bond breaks first, resulting in the formation of carbocation. So this is carbocation. So if you look at this, the stability order of carbocation is tertiary is the most stable, followed by secondary, followed by primary. This is the stability of cation. So now look at this, tertiary being the most stable cation. So these tertiary cation will be coming from tertiary alkyl halide. So the stability order of cation and the reactivity order of alkyl halide both are parallel. So I hope this point is clear. Why tertiary is most reactive? Because if this tertiary undergoes breaking of CX bond, this will give you the most stable tertiary cation. So if the starting alkyl halide is secondary, this will give you less stable secondary. If the starting alkyl halide is primary, this will give you the least stable primary. So for this reaction to shift in the forward direction, the stability of this intermediate has to increase. So the stability order is tertiary is the most stable. So the tertiary alkyl halide is the most reactive. So this is your RDS plus X minus is formed. Now look at this. In the first step, there is a formation of X minus. So these X minus and this positively charged cation should be stabilized by polar protic solvent. So there is a formation of charged species in the rate determining step. So these charged species can only be stabilized by a polar protic solvent. So this reaction is much more faster or feasible in presence of polar protic solvent. So I hope you got this point. Why solvent is polar protic? Because this has to stabilize the cationic and the anionic species. So these ionic species can only be stabilized by polar protic solvent. Next one more look at this. We have this equilibrium. In this equilibrium step, there is a formation of X minus sign. So from outside, if some X minus sign is added, then this will show common ion effect. So in all E1 reactions, successful E1 reaction, common ion effect of X minus is observed if we add X minus from outside. So look at this, if X minus ion is added from outside, the quantity of X minus ion, that is the product increases, so reaction shifts in backward direction. So this is what we call as Le Chatelier's principle, effect of common species. So this common ion effect observed also proves that in the first step or the rate determining step, there is a breaking of carbon halogen bond. In the second step, one more thing, whenever there is a formation of carbocation, this carbocation will try to rearrange to a more stable, so there may be chances for formation of an unexpected or abnormal product. So whenever in any given chemical reaction some unexpected or abnormal product is formed, so chances is there that the reaction proceeds via formation of carbocation, and these carbocation undergoing the rearrangement part. So keep this thing in mind. So in the second step we have this carbocation. Now these carbocation undergoes elimination. This carbon hydrogen bond breaks, means this electron is transferred between carbon and carbon, resulting in the formation of alkene plus H plus and is removed. So this is the alkene that is formed. So this formation of alkene will always follow Saint-Jeff's rule. So combining all these, the reactivity order of different halides, it is tertiary benzyl, which is equal to tertiary allyl group, which is more reactive than secondary benzyl group, secondary allyl, which is equals to tertiary alkyl. Then we have primary benzyl, which is similar reactivity to that of primary allyl or secondary alkyl cation, alkyl group, followed by primary alkyl group, etc. This is the reactivity order of different alkyl groups. Now let's take up some examples based on this information. Because example is more important to understand the product formation. So look at this. We have this tertiary, this is tertiary iodide, this reaction under E1 condition, that is in presence of water. So when this gives you this, that is Saint-Jeff's, because this gives you more stable cation, tertiary cation, followed by elimination to give you this. So this is Saint-Jeff's. Take this. Now we are starting with this compound. This compound reacts with methanol under E1 condition. Now in the first step, look at this. There is a formation of cation CH2, CHBr, CH2 and CH3. If you look at this is secondary. Now this secondary force undergoes a rearrangement by hydride shift. Hydride shift. By this hydride shift, we are getting a much more stabilized, resonance stabilized carbocation. Now आप ये पूछ सकते हैं कि ये यहाँ पे भी शिफ्ट कर सकता था, लेकिन अगर मैं यहाँ से शिफ्ट करता तो these type of resonance stabilized cation will not be formed. So only one option is left, that this has to undergo migration. Even after migration, we are getting secondary, but this is allyl. So if you look at this, we are getting secondary allyl, which is very reactive for this reaction. So finally this undergoes elimination to give you the resonance stabilized or conjugated alkene. So this is conjugated system. Like this, we have this benzene substituent CH2 CHI CH3. Now this is made to reactivate polar product solvent under E1 condition. So in the fourth step, there will be formation of cation. Now these cation undergo two different types of rearrangement. Look at this. By hydride shift from this side, we'll get this is by this hydride shift, or we also have this hydride. So by this hydride shift, we get this cation CH2 CH2. Now this is secondary, this is tertiary, but this is secondary and benzylic. So secondary benzyl is more stable than this tertiary alkyl group. So this is more stable. So this being more stable, this cation will be rearranged to this more stable cation. Finally, this will undergo elimination from this to give you again the resonance stabilized, that is conjugated alkene. So we have a conjugation. So whenever there is a possibility of formation of conjugated alkene will always be forming as a major product in E1 reaction. Now I'll take up a very specific example. Now we are starting with this alkene. So this is methyl group, this is CH2CH3. So we have Br. This is tertiary alkyl halide. Now this undergoes E1 reaction. E1 reaction कर elimination unimolecular. How many possible alkenes will form? Possible alkenes. I'm not asking you what is the major product, but how many possible alkenes will be formed from this? If this is meant to react with water, that is highly polar product solvent in presence in E1 mechanism. So E1 mechanism, we are saying reaction must follow carbocation intermediate. So let's start with this carbocation intermediate. Now look at this. This breaks minus Br minus. So we have this CH3 positive. Now if you look at this carbocation, this carbocation has got 3 beta hydrogen. So it is beta 1, beta 2. We also have a hydrogen here. So 3 possible alkenes will be formed here. So from beta 1, so this beta 3. From beta 1 we'll get this alkene will be formed. If we remove this beta 2, then the alkene formed will be, this is the alkene form. If this undergoes beta 3 elimination, then the alkene form will be, this is the alkene form. So this is product 1, product 2, product 3. Now these carbocation may undergoes rearrangement via the ring expansion, because we know the 6-member ring is the most stable ring followed by 5-member ring. So this 5-member ring will undergo ring expansion. So in this ring expansion, now look at this. This carbon-carbon bond is break, and this electron which was sharing within this carbon-carbon is transferred to this carbon. So E carbon क्या हुआ? Negative, and this negatively charged carbon is attacking the positively charged carbon. So this is what we call as ring expansion. So by this ring expansion, we are increasing the size of ring. So 1, 2, 3, 4, 5, 6-member ring is formed. And if you look at this carbon is having methyl and ethyl. So make it, this is methyl, this is ethyl. And look at this, the adjacent carbon is positively charged, so we have a positive charge here. So this is the rearrangement. So this 6-member is more stable than the 5-member ring. Now look at this, we have a beta hydrogen here. So this undergoes elimination here from this beta. यहाँ से elimination किया, तो we get this alkene. So this is product number 4. Now this is secondary. So these can be converted into tertiary. So now for this we have to undergo alkyl shift. So the first one, let's look at this. There is a possibility of methyl shift. If this undergoes methyl shift, ये methyl यहाँ से migrate किया. So what we get is, we have a positive charge here, then CH2CH3 methyl group goes here. Now this carbocation is tertiary, and if you look at this tertiary, there are various beta hydrogen. We have a beta hydrogen here, we also have beta hydrogen, we also have beta hydrogen here. So these may give you 3 different products here. So we have one product here. These may also give this product, elimination from this side, or these may also form this product, elimination from this side. So this is ethyl, this is methyl. In between these two we have this product. So this was first product, second product, third, fourth, fifth, sixth, seventh. Now if there is a possibility of methyl shift, then there is possibility of ethyl shift also. These may undergo ethyl shift, C2H5 shift. This is ethyl group. If these undergo shifting, then the product form will be, this is ethyl, this is methyl, we have a positive charge here. And again look at this, this is again tertiary, and this has got the three hydrogen, beta hydrogen. We have a beta hydrogen here, we also have beta hydrogen, we also have beta hydrogen. So again 3 possible products will be forming from this cation. So we have this product from this side, one product. Elimination from this side, we have this product. Then elimination from this side, this hydrogen, we have this product, methyl, ethyl. So this was 7th, this is 8, this is 9, and if you look at this, these 2 products, this is still the 7th product, product number 7, these are identical. So now the question is, during the lifetime of a carbocation, there are three maximum rearrangement is possible. So a carbocation cannot undergo infinite numbers of rearrangement because it has got its lifetime. So during its lifetime, in the reaction condition, only 3 times rearrangement is allowed. So these alkyl halide, on undergoing E1 reaction, 9 possible alkenes will be formed. These are the 9 possible alkenes. 1, 2, 3, 4, 5, 6, 7, 8, 9 possible alkenes will be formed. So this is all about the rearrangement of carbocations. So during the course of carbocation formation E1, there is always a rearrangement of carbocation. So whenever there is a possibility of rearrangement, there may be some abnormal products. So these abnormal is only because of the rearrangement of carbocations. So this is a brief idea of this E1 reaction. So one thing that we have to keep in mind is this point that we have to keep in mind. Suppose we have this tertiary alkyl iodide. Now this undergoes E1 in presence of highly polar protic solvent. So if you look at it, this is tertiary iodide, one of the most reactive for E1 reaction, but this does not undergo elimination. Even you keep on heating for a number of hours at very high temperature also, these does not undergo elimination reaction. So the reason is, in this E1 reaction, there has to be formation of carbocation. So this is a bridgehead. This is bridgehead. So bridgehead carbon cannot assume planarity. So this bridgehead carbon can never assume planarity. Since these cannot assume planarity, there is no portion of formation of carbocation. So cationic carbon is sp2 hybridized and it should be planar, but bridgehead carbon cannot assume planarity. So these cannot assume planarity. Since this cannot assume planarity, there is no question of carbocation formation. So every tertiary alkyl halide will not react. Only those tertiary halides in which halogen is not at bridgehead carbon will undergo reaction. If the halogen is present at the bridgehead system, then bridgehead system cannot assume planarity and no cation formation takes place and no E1 reaction or E2 reaction takes place. That is what we call as Braid's rule that I have mentioned in specific E2 reaction. So this is a brief summary of E1, E2 and E1cB. So this is the elimination reaction of alkyl halides. So alkyl halides will undergo elimination by these 3 different pathways. Out of this, the most common pathway is E2 pathway and the least common pathway is E1cB. So these 3 mechanisms or these 3 pathways is basically based on the different timings for breaking of carbon hydrogen and carbon halogen. In all these pathways, there is a breaking of carbon hydrogen and carbon halogen, but the timings are different. Based on this different in timing, 3 different mechanisms are proposed. One involves transition state, one involves carbonyl intermediate, the other one involves carbocation intermediate. So hopefully you enjoy this elimination of alkyl halides. We'll meet you again.